So we've been looking at sequences, and now for the rest of this chapter we're looking at sums of sequences or series. And you've seen this sigma notation before when we were looking at Riemann sums in Calc 1. Just a quick review. This is your index, tells where you're starting. Now for sequences I said the n represented where you were in the list. So it always went n equal 1, n equal 2, n equal 3. We kind of lift that restriction for series. You can re-index. This first index could be whatever. We might start at 5 or 20 or -2. It'll be an integer, but it may not start at 1. I've kind of written a standard form there starting at 1. A sub n is going to describe the terms of that series. And so in this case, we're summing up A1, A2, A3, A4 forever. All right, finite sums would not be interesting for a calculus class because you've known how to do finite sums since elementary school. But what does it mean to add up forever? And so we've sort of done this a little bit in Calc 1 when we talked about the limit as the norm of the partition goes to 0. We took some limits. It's a little bit trickier in general to do that. That's why we didn't always do integrals by the definition. But what we want to do is define what do we mean by this infinite sum. So we're actually going to define it as a sequence, much the way we did with improper integrals. So I'm going to define a sequence of what are called partial sums. The first partial sum, S sub 1, means add up all the terms up to the first term. So that's just the first term. So the second partial sum means add up the first two terms. The third partial sum means add up the first three terms, and so on. These partial sums will form a sequence. Right? And as you go farther and farther out in this sequence, you're adding up more and more terms of the series. So what we want to define as an infinite sum is the limit of these partial sums. This is very similar to what we did for improper integrals, where instead of integrating to infinity, which didn't make sense, we integrated to b, and then we took the limit as b went to infinity. Well, here, we're not summing up to infinity. We're summing up a finite amount, but we're taking the limit as you add more and more terms into that running total. You can think of those partial sums as keeping track of a running total. So we want to define a series to be the limit of these partial sums if it exists. And we'll say the series converges. If it doesn't exist, we'll say it diverges. By definition, the series converges to, we'll say, L if the limit as k goes to infinity of those partial sums equals L. If the limit doesn't exist, we're going to say the series diverges. So there's our definitions for series. What it means to converge, what it means to diverge, and what we're converging to. So we'll often just say that's what the series equals. So you'll just say the series equals L if it converges to that. So it still boils down to a limit and a limit of a sequence, right? So that's why we spend all that time on sequences, because they really are the underlying basis of finding sums of series. They really are limits of sequences. So if that limit of these partial sums, as you add up more and more and more terms, if that's heading somewhere, that's what we mean by that infinite sum equaling L or converging to L. If this limit doesn't exist, then it diverges. Now, this seems easy, deceptively easy, right? Oh, well, we know how to take limits of sequences. We should be able to just take the limit of the partial sums, and we'll have the sum of the series. The problem is getting this. I'll just write down here, given a series, coming up with a formula, right? You could always write out k terms, but in order to write this sequence as a formula, you would need to know a formula for the kth partial sum, and that typically is not easy. So we're actually rarely going to be doing it by the definition. We will develop theorems and properties that will allow us to avoid going to the definition. But in a minute, we'll look at what are called geometric series. And geometric series are one series where we can actually figure that out pretty easily, which then means we can easily just take the limit and figure out what the series converges to. So we'll look at that next time.